So for this session, that should be exactly the same. That should be good. That should be good. Oh yeah. We got my surface. This is yours. Or a clock in this place. Yeah, a clock in there.
That's stay there. It seems to disappear.
Yeah, if it disappears, just click where it was and it'll come back. Yeah, so
Okay.
when you're in your
That one disappeared once I had that chat with her.
yes.
So I just start a new canvas.
Yeah, just up to something.
Which, like, does this need turning on? So what do I do with that?
So it should be.
Yeah, that's on. Thank you. Good. Thank you very much. Good. Yeah. Thank you very much. Okay, let's get started. So I've ran the last two lectures rather slowly, so I'm going to have to catch up at some point, but I want to finish off lecture 2 first. So where we ended was the idea that there exists a fundamental equation that is only a function of the extensive parameters and that it is first order homogeneous. Second, that you have two different representations, either making energy primary or entropy primary. They're both equivalent. If you can find such an equation, it contains all the information about equilibrium states. So for your system, if you have a fundamental equation, you have everything. There is no more to be learned, okay? But the trouble is, fundamental equations are hard to come by, okay? So we will end up with 3 such equations in my part of this course. In statistical mechanics, you'll learn about a thing called the partition function, which gets you the same information, but in a much more general sense. Okay, good. Okay, so you can't get a fundamental equation usually. So instead, what you get usually is equations of state. So equations of state are not really a substitute for the fundamental equation, but they give you functional relationships. So you get functional relationships between state parameters. Okay, and you have a set of equations of state. Okay, not just one. And you need to worry. And what you have to worry about, what is dependent versus independent parameters. And you have to worry about degrees of freedom. So it's not as clean as the fundamental equation, but since you can't always get a fundamental equation, these guys just have to do. Okay, so we're going to have a few toy systems throughout this subject. One of them is the ideal monatomic gas. Another one is a simple spin system. And let's start with the first one. Okay. So toy systems. Example. So this one's going to carry all the way through the subject into Julian's part. So when it's ideal monatomic gas. It's a simple system. It's a very powerful system. And we can learn a lot by studying this because of its simplicity. Okay, so I've got a box. I've got gas particles in it. They're monatomic, they're point particles. They're all moving with different velocities. So first thing I need is state parameters. So we had these yesterday. We need pressure, we need volume, we need temperature, number of particles, energy. They're obvious. And we also need entropy and chemical potential. So if we have all of these state parameters, then we can fully characterize this ideal monatomic gas, okay? So what are the equations of state? Okay, equations of state. Any of you guys? Yeah. Ideal gas law is an equation of state. So EV equals nRT, if you like. I'm going to give it in two forms. So PV equals big N KT, and this is equivalent to little n RT. Okay, so this is number of particles, Boltzmann's, let me just label these. So this is number particles. This is Boltzmann's constant. Number of particles, really counting. Actually, let's get rid of that. So Boltzmann's constant and temperature. So in this case, number of moles. And there's two types of moles to make life complicated, and that is the universal gas constant. Okay, so that's one of my equations of state. Turns out I need a second equation of state. Okay, any takers on a second equation of state? Yeah, the energy one. Okay, so second equation of state is going to be U equals 3 on 2 N Boltzmann's constant T. And this is equivalent to 3 on 2 nRT. Okay, again, two different ways of looking at them, both equivalent. So all I'm doing is using different units. Do we need a third equation? What about entropy, chemical potential? They seem to have gotten left out. Okay, I can get an entropy equation. I'm not going to at the moment. What this boils down to is this issue of dependent, independent, and number of degrees of freedom. So I don't need it because 2 is enough to fully describe this system. I can extract entropy, but it's a lot more work. So they're my two equations of state. I don't like these because I have extensive. So extensive is volume, number of particles, energy, number of particles. I have intensive. I've got pressure, temperature, temperature. So this is a mess. So the way that I'd like to do this is to rewrite them as intensive parameter equals a function of extensive parameters, okay? And later you'll see that this is actually not just niceness, it's important. Please, please, Mr. Pewter. Good. Okay, so rewrite. As intensive equals function of extensive. So in the formalism we'll develop, this is important. So if I do that, the first equation, PV equals NKT, I've got P and T are my intensives. So I write P divided by T is equal to N K 1 on V. So I've just shuffled it around. So I've got intensive equals function of extensive, and I've got 1 on T is equal to 3 on 2 N K 1 on U. So these are my equations of state written as I would like them. Okay, entropy has disappeared. If I asked you to take a guess, which representation am I using? You've only got 2, so you've got a 50-50 chance of getting it right. I'm not using energy representation because energy is in the equations. So in the entropy representation, you have, entropy is a function of energy, number of particles, and volume. This is entropy representation. I also gave you conjugate pairs before in the energy representation, i.e. entropy goes with temperature, etc. But here I've got entropy representation. So the pairings are now different. As you'll see, volume pairs with pressure on temperature, energy pairs with 1 on temperature. So we'll get to this, don't worry about it. But you get different pairings for the different representations. Okay, so this is a complete thermodynamic description of a monatomic ideal gas. Okay, so we've got that far. So this is toy system number 1. Toy system number 2 comes sometime next week. Okay, so this fully describes my equilibrium states. And these are the states that I can study. But if I only study equilibrium states, it's rather boring because I really want to see things happening, not just sitting there staring at something in equilibrium. So let's see, thermodynamic processes. Okay, so as I said, all equilibrium states are described by fundamental equation. Okay, so either U, S, V, N or S, U, V, N. Either one. So as a mathematician, you guys need to be mathematicians if you're going to be physicists. There's no escape from that, even if you're a hard experimentalist. This describes a thermodynamic configuration space. Okay. And it is spanned by extensive parameters. Okay. So beautiful. We can now use mathematics of functions of several variables. But the news is not so good. So for single component system, so I only have one component, I get U is equal to some function of S, V, and N. What's the problem with that for a human? Yeah, there's 4 of them, 4 dimensions. So 4D, ick. So I would like to draw pictures of this. This is the simplest system, one component, and I'm already in 4 dimensions. So it's painful. So I don't know what to do. So I have U is a function of S, V, and in some other dimension, N. So this is my 4D blackboard. So the equilibrium states will be a manifold in this space. So let me draw a manifold as best I can. It'll be some kind of a surface, a 3D surface. So these are my equilibrium states. So equilibrium states, and they give me a 3D manifold in 4D configuration space. Okay, so I can't really draw this, but it still helps me to think about it, to know that the equilibrium states are a manifold in this space. One really important thing, note, I cannot represent non-equilibrium states here. Okay? So cannot do that. So all I can represent in this configuration space is equilibrium states. If something is not in equilibrium, these parameters are going to be ill-defined. So can't represent it at all. Okay, although we will not use this, apart from just thinking about things, we can actually make projections of this space that will be useful. And we'll do that all the time. But the rule you have to remember is only equilibrium states. Okay, if it's non-equilibrium state, can't show it. Don't know what to do with it. Okay, so what I'm interested in is paths on hypersurface. Okay, I'm mixing my terms. Manifold. Okay, so it's a hypersurface, but it's a manifold of equilibrium space, of equilibrium states. Okay. So I've got my space with some other variable, U, S, V, N. I've got my surface. There's my manifold. So if I start at state A, and if I have a state B, I can have some process, A to B. Okay, so the path A to B represents series of equilibrium states. Okay, so I have here a process that changes states. From A to B. Okay. So if all states equilibrium, that implies I get a continuous path. Okay. So question for you guys. What about A to B via non-equilibrium states? What do I do then? This is continuous. So I'm in an equilibrium state here. Disappear, reappear over here. Disappear, reappear over here. You get a bunch of dots joining up equilibrium states. So I get basically a series of dots. Dots. As long as I wait until I get to equilibrium, okay? So basically I get the same diagram. I'm not going to draw the whole thing again. And I have equilibrium state A, equilibrium state B, and I'll have maybe a dot here, maybe a dot here, maybe a dot here. Depends how I do it, okay? And I'm heading that way, okay? So that's as good as I can get. Yeah. Yes. Yeah. It's not represented in this space at all. You can have such a state. I mean, you could design a state where you included the velocity and position of every single particle, 10 to the 40, no, 10 to the 150 dimensional space. Yes, it would be a continuous path there, but it would not be this space. It would be a different space. Yeah. Only in this space, only equilibrium states. Okay? Does not include non-equilibrium, does not describe them, knows nothing about them. Okay? Yes. Okay, what I have to do, I'll get to that in a second, okay? So we'll get to that. I need not have any intermediates. I could just be at A and then break a chamber and wait and get to B, okay? There need be no intermediates on this thing. Intermediates here have to be equilibrium states. Okay. So, on that. Okay, so here's where I invent a new idea, quasi-static process. process. The whole of this game is based, a lot of it, based on the idea of a quasi-static process. So idea, keep system in equilibrium state during process. So I can't keep it in an equilibrium state as close as possible. Okay. So I want to keep it as close as possible to equilibrium at all times. So what this means is I need to make very small changes in state and move slowly. Slowly, such that system keeps attaining equilibrium. Okay, very small steps, very slowly. So this is my quasi-static process. Okay, how slowly? Well, that depends on your relaxation time, okay? So if your relaxation time is fast, you wait a couple of relaxation times and then make a change, small change. So example, actually you give me an example. Quasi-static process. Something that's going so slowly, yes. Yep, gas expand really slowly, piston slow, yes. Helium leaking out of a balloon. These are all good examples. So examples. I like that one. Okay, quasi-static process. This is going to be central. So everything we try and do is quasi-static. And slowly is a terrible word. Move slowly. Defined by relaxation time. That tells you how slow you have to move. Always get back to equilibrium. So what I get from this is in the limit, as step size goes to 0, I get continuous process. Okay, but in reality, I'm going to have my hypersurface. So this is again entropy, sorry, S U V N. I'm going to have some path of dots. So I start at A and I move lots of dots very close together to B. Okay, that's my quasi-static process. Is a quasi-static process in the limit as you get steps smaller and smaller and smaller a a reversible process or not a reversible process? If reversible, give me an argument why. If irreversible, give me a counterexample. Had a counterexample already. It's irreversible. What's the counterexample? Correct. The helium balloon case, you can't put the helium back in. It's quasi-static, but it is not reversible. So quasi-static is essential for reversibility, but it's not sufficient. So I can write reversible implies quasi-static. But quasi-static does not imply reversible. So example is the leak, helium balloon leaking. That's irreversible. But quasi-static. Okay, so always want a quasi-static process, but it's not enough for reversibility. Reversibility needs more. Okay, so let's write some words about all that. Reversible process. I get, it's got to be quasi-static. As we will see later, the change in entropy from A to B will be equal to 0. And real processes only approximate this. Okay, all real processes are irreversible, no matter what you do. There'll be some gain in entropy. You cannot avoid it. Irreversible process. This guy doesn't care about quasi-static. Could be quasi-static. Or not, doesn't care. Delta S from A to B is going to be strictly greater than 0. All real processes. Okay, so we're going to learn thermodynamics, but I'm telling you straight away that all real processes are irreversible, and that my fundamental equation tells me nothing about non-equilibrium states. Why is thermodynamics of any use whatsoever? What's the trick we're going to play all the way through this subject? So all this subject tells me is I know about equilibrium states. That is all. Yeah. Okay, so this gentleman says, just focus on the two end states. Because the end states are strictly characterized by their extensive parameters, how you get between state A and state B does not matter. So the real process will be irreversible. I can't analyze that by thermodynamics, but I find an equivalent process that is reversible that gets me from A to B. And by analyzing that, I learn everything that I need. So this is going to be the trick. So what are we going to do? let me use a new piece of board. So trick, we have state A, state B, we have an irreversible process. And so what we do instead is we find reversible process A to B. And since two equilibrium states defined, or no, not defined, don't like that. Fully described by extensive parameters, params. This implies I will understand, I will be able to get the process. I'll be able to figure things out. Okay, so always the trick is going to be find something that is reversible, because that one I can understand even if I can't understand anything else. Okay. I do want to mention the types of processes. I'm really going far too slowly. So this is just the catalog, categories of processes. So again, these are simple processes, but if all I know is I have a start point and an end point, I can break it up into any reversible path I like. These are obvious. Some of them are, some of them aren't. Isothermal. That means T is constant. Isobaric. And that means P equals a constant. Strange one again, isochoric. V. Say again. As you wish, okay? And adiabatic, they all have multiple names. Adiabatic means, this one's a bit strange. The Q equals 0. So this means no heat exchange. Heat exchange with environment. Okay, all of these will have multiple names. What is the name you gave for isochoric? So this is equal to isovolumetric. Equivalent, what's this one equivalent to? Anyone know? We'll see it later. Isentropic later. Okay, isoentropic, but isoentropic sounds terrible, so they just made it isentropic. Okay, we've finished lecture 2, so we're almost a full lecture behind. Any questions or any of that? Because this is really the foundations of everything. Okay, the question is, real processes, always irreversible, but do they sometimes look reversible? Okay, let's take an example. I take a cylinder of gas with a piston in it. Instead of dropping okay, let's do the experiment better than that. Cylinder of gas with a piston on it. Next to it, I put a tiny bookshelf that has millions of shelves. On each shelf, I have a grain of rice. So when I have the piston next to the first shelf, I just push the grain of rice across and it drops down. It's now aligned with the second shelf. I push the grain of rice across. I keep going all the way to the bottom, push the last grain of rice across. If I now try and reverse that process, what you will find is that at the end of putting them all back to where they came from, I think I will be 1 grain of rice short. I will not quite get back again. So it's going to be irreversible, but irreversible by the effect of 1 grain of rice. So now if I make the grain of rice smaller and smaller and smaller, I can make this closer and closer to reversible. Just a small change in state. So the gravitational impact of putting 1 grain of rice on it, a little bit more pressure. Okay, let me repeat that. Basically, all I'm doing is increasing the gravitational force downwards by having a little bit more mass. All I'm doing is incrementally increasing mass. Equally, I could just put grains of sand on it, okay? 1 at a time, slowly pushing it down. The reason for having the elevator is that I can reverse it, so I can push them all back to where they came. Yeah. Yes, classical spring is fine. Same. Yeah. Okay, so this gentleman here says classic spring is another example for you guys online. Yes, classic spring, you have it starting to oscillate and it almost comes back to the same place, but it doesn't quite. Each time it's losing a tiny amount of energy because of friction and other dissipative processes, and it's going to be almost reversible, but not quite. Okay, so losing stuff to friction is one way of thinking about it, but not always. I think the gas one is not quite losing. Well, it always will end up in heat. Energy is conserved, so you'll always generate heat. Yes. We'll get to more of this. Okay, people online. As far as I understand, we are now fully live. Hybrid is actually not necessary. So please come to lectures. One thing I should announce right now is that there are 2 issues. Mid-session test. This will be live in class on paper. So there is no electronic option unless you are overseas and have special reasons. So please, you have to start coming into classes. And the final exam is the same. Same. So please start attending. Okay, so this is unapologetic. University policy has changed. They've come to the realization that hybrid is not pedagogically sensible, okay? And that there's a reason for lectures. And the lecture going so slowly is because we're interacting. You're asking me questions. That's the whole point of being here. Yeah. Not for me. I'm absolutely closed book shut down. What I will do instead is I don't believe in memory. You'll have a full formula sheet that says what it's about. Anyway, let's deal with that later. Yeah. Yes. Oh, okay. So so the question is, isn't it hard to find an equivalent reversible process between A and B to characterize the irreversible one? You'll see the trick, it's a bit more subtle. So the process from A to B will still increase entropy, for example, but we will not just find a path, but we will couple the system with a special environment or another system so that overall there is no change in entropy, but by coupling two things together, we can characterize it. You'll see how it works, okay? It works very well. Yes. Can we have a quasi-static process induced by the surroundings? Well, yes, my elevator of grains of sand would be such a thing. Okay, so the person says relaxation process depends on the system, not on the surroundings. How would that work? Yes. So in a sense, with your leaky helium balloon, it is the system that is leaking out atoms, but it's actually the boundary that has tiny holes that lets them out very slowly. So it is boundary dependent, not system dependent. The boundary is almost completely impervious, so only occasionally an atom goes out. If I have a boundary with big holes in it, it's not going to be quasi-static. Think about it. Let me get to kinetic theory. I think, so I'm saying boundary influencing in the leaky balloon. Can we have surroundings? Probably, but I can't think of an example offhand. Yes. Radioactive isotope is the example brought up. So that's spitting out particles very slowly. It's possible that that would work if it's just throwing them out occasionally. I think you've got to cook up examples, okay, and think. Okay. In-person stuff. Okay, yeah, that was a while ago. Okay, that's been there for a while. So kinetic theory of gases. We're not going to get far today. So the aim of this is to link. So this is lecture 3 proper. So the idea of this is to link microscopic with macroscopic. It's something we won't use again, but it is important. So I can write pressure due to gas. So I take my toy system, which is cylinder, hard walls with a piston in it that can move. So that's my piston. And I apply a force to that, F external. I've got a cross-sectional area, and I've got a volume, and I've got gas particles in there banging around. They're all moving. Okay, so at equilibrium, at mechanical, I can say that pressure of the gas is equal to minus the external force divided by the area. Is the area. So that's my mechanical equilibrium condition. What is going on inside the gas? So the gas is providing pressure That's my piston wall. By having particles come crashing in this way, velocity, hit the wall and bounce off. Okay? So this is V dashed coming off. And it's moving in that direction. Okay, so they bounce off wall. Okay, so what do I want? I want elastic collisions. Implies change in energy equals 0, but I get a force equals the change in momentum. Okay? So what is my momentum? P is equal to mass Vx, Vy, Vz. They're my components. And change in momentum is going to be equal to -2 the mass Vx. So I'm assuming this is my x direction that way. And that's a vector. So I've got a unit vector I hat. Yeah. Okay, so for the wall, my change in momentum of the wall is going to be equal to plus 2m Vx per particle. Okay, so I've got particles battering the wall. Each of them is imparting a very small change in momentum. So I need to calculate how many particles are hitting the wall. Go, go, go. So number of particles hitting wall. So it's going to be dNc dt. So how can I deal with this? I've got a piston. I'm going to take an imaginary volume here. That's going to be, go away. That's going to be Vxt. And I've got a particle coming in that way with velocity x component Vx and bouncing off. So using that funny little space there, I can say NC, number of particles colliding, is equal to a half because half go left, half go right. The number of particles divided by the volume, Vxt times the area. So half, since half go to the right, that's the density. This is that space. So if I just use that, I get that dn colliding, dt, it's a very easy derivative, half n over v Vxa. That's a nice equation. Okay. Last thing. I'll continue this tomorrow. What is wrong with that argument? Yeah. So answer was assuming Vx is constant. I'm not actually, but it is a problem. That means for every single particle, Vx is going to be different. You're in a distribution. We're going to solve that tomorrow and next Friday when we just take expectation values and it'll all come out nicely in the wash. Okay, so we've gotten to that point. I want to push this further on Friday to end up with a link between atomic description and the equations of state. Okay, leave it there. Good. Midterm is during class time. It'll be on a Friday. Yeah, it'll be the lecture. Okay. Good. What am I doing here? Hey, fantastic. No problems whatsoever. I've got to now kill this somehow. Stop share. And then end.